So last night you did your molar mass video lesson, so a little bit of these notes we're going to skip a couple of slides because we did do the molar mass. And as promised, it's not hard, right? Molar mass was not hard. So we talked about it in the video. A mole is a counting number, okay? You can have a mole of anything. What we are going to use in here are these units right here, the atoms, molecules, ions, and formula units. Those will be what you see throughout the course. If we're talking about an element, we would say we have 6.02 times 10 to the 23rd atoms in a mole. If we were talking about compounds, we would say, if we're talking about molecular compounds, we would say molecules. If we were talking about ionic compounds, which y'all don't know what those are yet, I know, we would say formula units, okay? So in the video we said it's they were saying 6 times 10 to the 23rd on the little mole song video, but technically it's 6.022 times 10 to the 23rd. We tend to use 6.02 times 10 to the 23rd in our calculations. It doesn't rhyme very well in the song, so they just said 6, you know. Yeah, it doesn't quite work, yeah. So that is actually called Avogadro'S number. Most chemistry students call it avocado's number. Y'all aren't the first to come up with that. That's like a standard thing. So that's the Avogadro's number. It is a counting number. Just like if I were to say I have a dozen cookies, how many cookies do I have? If I have a dozen donuts, how many donuts do I have? 12. If I have a dozen eggs, I have 12 eggs. So the unit of mole means 6.02 times 10 to the 23rd of whatever I'm talking about, okay? And in the song, it gives you some funny little things if you had a mole of marshmallows and pennies and all that. So it's a huge amount, okay? But we're talking about atoms or molecules which are so incredibly small that you actually could hold a mole of them in your hand. That's how small. It kind of gives you an idea of how small an atom is. For instance, one of the quizzes, well, it talked about sugar, okay, in the video. We'll talk about that. The formula for sugar is C12H22O11, which is table sugar, which is got a molar mass of 180 grams. So I could go into the lab, get my balance out, and I could mass out 180 grams, and I could hold that in my hand, and it would contain 6.02 times 10 to the 23rd molecules of sugar, all right there in my hand, okay, because they're so small, which is why we have such a number to kind of talk about it. So if I have 6.02 times 10 to the 23rd molecules of sugar, I have 1 mole of sugar, and then since the molar mass is 180, actually it's 180.18, then that would be all equivalent. So we're going to use that as a conversion factor. So last night when you were doing the molar mass, we don't just calculate molar mass. That is like one step in the process, and that is to use as a conversion factor. So whenever we calculate a molar mass from our video last night, it is grams per 1 mole. Anytime we see something like this, like this right here, that is always per 1 mole. So you're never going to put anything in grams per mole other than a 1. Okay? So whenever you figure out or calculate what the molar mass is, that value always goes with the G for grams. Okay?
Wait, so why would a whole mole of copper only weigh 63 grams?
Because that's what it's defined. Because 6.02 times 10 to the 23rd atoms, which is equal to a mole, would have a mass of 63.55 grams. Yeah.
I was thinking
You were thinking atom. Is that what you were thinking?
I was just thinking, how is that much copper?
So actually 63.55 grams of copper is actually not that much. Yeah, it's not.
I know, but wait. Oh, okay, no.
Okay.
So 6.23, whatever.
All right, so let's, we already know how to do molar mass because we watched our video lesson. If you did not watch your video lesson, then number 1, you should, because you need to know how to do it. And number 2, I don't look forward to grading your quiz if you didn't watch it.
I got 100 on my quiz.
Okay. All right. So we don't need to do that. We don't need to do that. So now we're going to use our conversion factors. So I do need to tell you about our diatomic molecules. And what does the word diatomic mean to you, if you had to guess?
Two atoms.
Two atoms stuck together. Okay? There are some of the elements on the periodic table that do not exist by themselves in nature. They need a friend to go around in the world with, and those are our Brinkelhoffs, is what we call them, because it's an easy way to remember. But it's the elements that are considered to be diatomic. And that's why we do it, just to help us remember. What that means is, when they are by themselves in nature, there's two of them stuck together. Life is better with a friend, right? Okay. So what that means for us is when these elements are by themselves, for instance, if I was to say I have oxygen gas, that means I write it as O2. So right now we're breathing in oxygen. We are not breathing in individual oxygen atoms. We're actually breathing in a molecule of oxygen, which is two oxygens stuck together. So in terms of molar mass, if you look at your periodic table, it says the molar mass of oxygen is 16. But for oxygen gas, we would write 32. We would double that. Yes?
What happens if oxygen was out on its own without a diatomic bond?
It can't exist. It doesn't. Now, in a compound, oxygen can be anything it needs to be, any number it needs to be to bond correctly. So in a compound, we would just use 16 to add up a molar mass.
Okay.
But when it's by itself, when any of these things are by themselves, they're doubled. Okay? And all of those are gases except for bromine. Bromine is a liquid. Oh, just kidding. Iodine's a solid. Duh. I don't know why I said that. Most of those are gases, with the exception of iodine and bromine. Bromine's a liquid at standard state, and iodine's a solid. Okay? So those are, you'll hear a lot about Brinkelhoffs. If you go ask any old chemistry students in the last year or two that's been in my class, and if you ask them what are the diatomic molecules, they should be able to tell you Brinkelhoff, but we'll see.
But I feel like when I think Brinkel, I think K and not CL.
But it's Brinkel, coal.
Oh,
Oh,
I don't know.
Otherwise, it'd be Brinkhoff.
Oh, Brinkel. I'm there. Sorry. It like spells it.
By the way, I am recording, so if someone just got your light bulb moment.
Oh, sorry. Sorry to whoever is listening. Maybe dumb.
You think they figured out who it is? Okay.
They-
All right, so this is the mole map. This is the mole map. You can use it or you cannot use it. It's just a way to help you remember. If you need to go from mass to moles, what are you going to do? If you're going mass to moles, you're going to multiply by the molar mass. If you're going to go moles to mass the other way, you divide by the molar mass. But if you are letting your units be your guide, do you need the mole map? Say no.
No.
So sometimes I hesitate to show the mole map because it's a little bit of a crutch. But if you need it, you obviously can't get it on a test. But if you're working through this and you forget, go back to this to see what you're supposed to do. But if you're letting your units be your guide, then you don't need this map. It's like if you know the way to Dallas without the map, you just get in the car and go, right? Well, you don't drive yet, so. All right, so we're going to do this. We're going to take 120 grams of calcium and we're going to take it to moles. So we want to convert that to moles. So we start with 120 grams of calcium. We want to get rid of grams, so where does it go in the next step?
On the bottom.
On the bottom, grams per mole. And look up on your periodic table, what is the molar mass of calcium to 2 decimal places? 40.08. So now my grams cancel, so I'm going to be left with moles. And before we write down our answer, how many significant figures do we need our answer in? 2, because of that right there. So, someone do your handy-dandy calculator and tell me.
2.99.
I've got to put it into 2 decimal places, though.
3.
Not 2 decimal places, 2 significant figures. So it should be 3.0. I think it comes out to like 2.994, but when I need 2 significant figures, that makes it 3.0. Okay? Let's do another one. I'm not just going to show it to you once and then say go on about your merry way. Let's do another one. Now we have how many grams of sodium? This should be sodium chloride. That word got left out. Although we could figure out how much sodium is in there, but we're not going to be that complicated yet. In 5 moles of sodium chloride, so we start with 5.00 moles of NaCl. NaCl. Yeah. I want to get rid of moles of NaCl. So where do I put it?
On the bottom.
On the bottom. And grams on the top. So now I need to calculate what the molar mass of NaCl is. And we have sodium is 22.99, right?
35.
So we do 22.99 plus 35.45. This is sodium, this is, and that becomes 58.44. 58.44. Moles cancel. And then we're going to be left with grams of NaCl. And who is my calculator today? And how many sig figs do I need?
Need 3 sig figs.
I do need 3 sig figs because it's 5.00, so that's 3. And I heard someone say it, 292. Thank you to whoever said that. Was that you, Megan?
Yes.
Thank you, Megan. H. All right. All right. So that's how you do grams to moles, moles to grams. So if you go back and look at the mole map, it will prove to you that when we are going grams to moles, we divide it by the molar mass. When we're going moles to grams, we multiply by the molar mass. But do we have to memorize that? Not necessarily. We follow our units. I promise you if you'll do that throughout this class, it will pay off. It'll pay off in physics as well. Okay, let's do some with, well, this is the same problem. I'm not going to do it because we need to finish up with time, but you can go back and work that out. I believe by memory, if you want to go back and work it out, I could be wrong, but I think it was 0.878 moles. But I'm going to put a question mark because I'm going from memory and I'm old. So, memory's the first thing to go. That,
And hair.
not always.
Not really.
No. All right, now we're going to talk about atoms and not that atom. Okay?
Yeah.
So we have 4.25 moles, of silver. We want to get rid of silver, so where does it go? Mole of silver. And how many atoms are in a mole? 6.02 times 10 to the 23rd atoms of silver. Cancel, cancel. So we're going to take 4.25 times 6.02 times 10 to the 23rd, and we're going to get an answer. And how many sig figs do we want to put it in? 3. Notice we look at what's given to us in the problem to decide that. So, who's got that for me?
2.56 times 10 to the 24th.
2.56 times 10 to the 24th. Did anybody else get that to agree with him? We should always double check ourselves.
I got it.
You got it?
Yep.
All right. So that's how you go from moles to atoms.
That's a lot of atoms.
That is a lot of atoms. Yeah. Well, I mean, it's over 4 moles, so it's a lot of atoms. All right. Now let's go from atoms to moles. We're going to do one of each kind here today. This wants to know how many well, that one's the same one, so that's a repeat, so we're not going to do a repeat, right?
Right.
So now let's do how many moles are in this many atoms. So before I even look, do I expect, with this number right here, do I expect more than 1 mole?
Yes.
Yeah.
By golly, I do. That's a way to kind of know where you're going, because if you did it incorrectly and you got less than a mole, you'd think, oh, I did something wrong. That number doesn't make sense. Okay? I want to get rid of atoms, so what goes on the bottom? 6.02 times 10 to the 23rd atoms per mole of sodium. So atoms cancel out. I'm going to be left with moles of sodium. Still need 3 sig figs. So what do you get?
1.37.
Say that again?
1.37 times 10 to the 47.
Nope.
I don't know.
Then you might have you probably just plugged it into your calculator incorrectly. Exponents in the calculator are a little bit tricky. on the classroom set, that is this kind of problem when you have an exponent on top and bottom is a really good time to use that N over D key.
I got 13.7.
Anybody else confirm that?
Yeah, I got that.
Then yes, we go. There we go. Okay. Did you use the N over D key or did you put parentheses around your exponents? Yeah, you either got to put parentheses or do that N over D key. Because if you have to be careful with the way you type it in. If you're having trouble typing it in after we're done with the lesson, I will come over and help you type it in the calculator.
What's D key?
Huh?
N
N over D key. I'm saying it really fast, so it might sound like I'm saying N over D. But if I say it fast, yeah. All right. Now, 2 steps. We're going to do the 2-step now, and not the fun kind. No, this is just kidding. Now we're going to go from one side to the other. We're going to go either atoms to grams or grams to atoms, which means we're going to need to go through the mole. Okay? You can't go directly from grams to atoms or atoms to grams. You got to go through the mole. He's the middleman. He's the middle mole.
Oh, that's so cute.
So 3.99 grams of potassium. I want to get rid of grams of potassium, so what goes on the bottom? Grams of potassium. What is the molar mass of potassium? 39.10. Okay, I've gotten rid of grams. Now I'm in moles. Now what can I do?
6 times 6.
And every 1 mole of potassium is 6.02 times 10 to the 23rd atoms of potassium. All right, moles are canceling, so I'm going to do 3.99 times Avogadro's number equals, and then divided by 39.10. Who? Avogadro was a famous chemist. He didn't actually come up with the number. They named that Avogadro's number in his honor. Somebody, I don't know if it was in this class, but someone got Avogadro. You got him. There you go.
You did?
Mia's got Avogadro for her scientist project. His name was Amadeus Avogadro, which is a really cool name if you ask me. He was not the most attractive looking man.
You know, my scientist's name was Kurt, so
Yeah.
it's not really a fun name.
Yeah, Amadeus is a cooler name. Yeah.
Positive I did this completely and totally wrong.
Okay. It should be a decimal, and the reason it should be a relatively small decimal because not a decimal. I'm sorry, because we're doing atoms. I'm sorry. It should be less than 23 though on the exponent.
Yeah, I got 6.14
I got an
times 10
exponent
to
of
the
20.
22nd.
Yeah, that's what I got.
Tell me what you got, Sean.
Oh no,
6.14 times 10 to the 22nd.
Hey, I did it right.
Yeah. So when I said decimal, I meant to say smaller than that because we have less than a mole when we know we have 3.9 grams. So that's how many atoms we would have. Okay? Now we'll do one going the other way. We'll go atoms to grams, just so you can see it. Okay? Before I move on, does everybody have this written down?
Yeah.
All right. Perfect. Next page, please. How many grams of helium are in 3.03 times 10 to the 21 atoms? So again, we're going to ask ourselves before we even calculate this, what is the molar mass of helium, by the way?
1.01.
No, that's
Helium.
hydrogen.
Helium. That's hydrogen.
I don't know.
So it's 4. So we have 21. So should we have much less than 4 grams? Yes, we
You
should.
only put 2.
Because I stopped to circle. Yeah. So we have atoms of helium. I want to get rid of atoms of helium. So what do I put on the bottom?
6.02.
We're going to finish this problem. I know the bell rang, but 6.02 times 10 to the 23rd atoms per 1 mole. And then 1 mole is 4 grams of helium. And someone do that very quickly so we can get an answer, and then y'all can go to lunch, 5th period. Sean has been our super duper calculator today. Special thanks go out to Sean Ryan for calculating.
Sean.
This one should be a decimal, right? 0.0 what?
201.
201. Justin beat him to the punch today. and that is grams.
Unless I did my numbers wrong.
Okay.
I got something good there.
All right. That paper you picked up today is not homework. You get to work on it all during class tomorrow so that if you need to ask questions, you may ask me questions. No homework.